Hello everyone. In this video, I will be explaining how the ADS-B protocol works and how PPM, also known as pulse position modulation, is used in its signal transmission. Initially, I planned to work on transmitting a color image, as I mentioned in the last video, but I found that it was less engaging in terms of signal processing and wireless communication concept. Instead, I decided to focus on PPM and its actual application in ADS-B. Moving forward, I plan to explore further implementations using Python and MATLAB to deepen my understanding of real-world communication systems. Now, let's do this. ADS-B, or Automatic Dependent Surveillance Broadcast, is a technology used in aviation for real-time aircraft tracking. It allows aircraft to broadcast their position, altitude, velocity, and other data to air traffic control and other nearby planes. Unlike traditional radar, ADS-B doesn't rely on ground-based systems. Instead, aircraft use GPS to determine their position and then transmit this information via radio waves on 1090 MHz or 9078 MHz frequencies. Now, let's talk about PPM, or pulse position modulation, which is the modulation scheme used in the ADS-B signals. PPM encodes information by varying the position of pulses within fixed time slots. Each pulse shift represents a different binary value, making it a simple yet effective modulation scheme for ADS-B signals. In ADS-B, PPM is used to transmit mode S messages, which include an 8 microsecond preamble followed by 112 bits or 56-bit data blocks. Now, before we go to the actual Python code, let's briefly review how does the PPM is encoded. The version of PPM we are using works similarly as on-off keying, but instead of just turning on and off, we encode data based on chip transitions. In our encoding scheme, each bit is represented using two chips, with each chip lasting 0.5 microsecond. This means each bit occupies a total duration of 1 microsecond. Here's how it works. If the chip starts at 1 and then drops to 0 after 0.5 microsecond, it represents bit 1. If the chip starts at 0 and then rises to 1 after 0.5 microsecond, it represents bit 0. Now, let's move on to the Python simulation. We have implemented a function called bits to chips that converts a bit sequence into our custom PPM modulation format. This function ensures that each bit is correctly mapped into chips based on our encoding rule. Wait, before diving into the full ADS-B packet, let's talk about the preamble. The preamble is crucial for synchronization. It allows receivers to detect and align with the signal. In ADS-B, you always need to identify 4 pulses of chips at specific time instances. The first one at the beginning of the preamble, so at the 0 microsecond. Second one at the 1 microsecond. Third one at 3.5. Last one at the 4.5. With a total preamble length of 8 microseconds, this pattern ensures the receiver can log on to the signal before decoding the data. And here's it. This is a visualized version of an ADS-B packet generated using on our Python simulation. Isn't it cool? You can clearly see the structured pulses representing both preamble and the modulated data. Now, let's see how we can transmit this kind of the packet into our SDR system, and then let's see if we can really decode this one and restore the original information. For the convenience, I have set the original data length to 10 bits. Since each bit is mapped to 2 chips, this means our total data packet contains 20 chips after the modulation. And here's what my ADS-B packet looking like. We have a preamble in the front of the data packet, and then after that, we have all the data packets modulated using chips. Now let's take a look at what our receiver received. As you can see, the signal looks very distorted. This is because of the noise introduced in the wireless channel, which affects our received waveform. But don't worry, we're going to fix this step by step using a structured signal processing pipeline. The key steps in our receiver processing include the timing recovery. First, we perform timing recovery to correct sample timing errors. By plotting an eye diagram, we can visualize how well the received pulses align and determine an optimal sampling point for the decoding. As you can see from here, before we do the simple timing recovery, we do not have the maximum point of the eye at the 0. But after we do the simple timing recovery, we see the center of the eye is now aligned at the point 0. Next, we apply frame synchronization. We need to detect the preamble in the noise signal and align our receiver's frame so that we can correctly extract the transmitted data. As you can see, the detected peaks means that when the two preambles are exactly aligned each other. So we can set this point as to be a starting index of the data symbols. Now, this is the result of the frame sync. So at this point, you may easily visualize that there are the preambles in the front of the packets, and then after that, they are the data symbols. And you may assume that at this point, we can decode all the information correctly, but we have few more steps to go on, which are the CFO correction and the channel equalization. Now, let's do this. Channel equalization and CFO correction. So after we do all those steps to correct the channel and correct the CFO, we are having finally some kind of meaningful data that we can decode. But before we actually decode this one, we need to apply the threshold. By applying the threshold detection to determine whether each received pulse represents 1 or 0, then we can successfully decode the original transmitted data. So I have applied the threshold to be 1.1. This can be any values that seems reasonable. So if I apply the threshold 1.1, we have this kind of the discrete value that we see in the TX side. And if we get the information from these values, we can stem plot the restored chips using PPM. And then since we have a stem plot, we can decode this one into bits again using the chips to bits, which is exactly inverse of what we did in the TX side. So by doing this, we have now the decoded bits that are same as the original bit sequence. Today, we demonstrated how the ADS-B and PPM signals can be effectively received and corrected using signal processing techniques. In future work, I plan to implement these recovery steps in MATLAB and using the SDR device, exploring more advanced wireless communication algorithms. And also, I plan to actually implement this one to visualize the tracking of the aircraft. So, I hope you will have a good day, and I'll see you in the next video. Bye bye.